In this video, we're going to look at Cayley's theorem, and I mean we're going to first motivate it. So this is really a motivation of Cayley's theorem. All right. So let me write it fully. What the heck? It's good to be proper. So we're going to think about Cayley's theorem, and I mean, it usually looks pretty abstract, so we just want to try and understand it. So a really cool way to understand Cayley's theorem is to start by looking at a specific type of group. Let's look at the group, how about Z mod 5Z star? Or let's say Z mod 5Z and a multiplication. Alright, so if you're not familiar with what this is, we're just going to call it G. That way we don't have to keep referring to it all the time as Z mod 5Z star. But this group here consists of the elements 1, 2, 3, 4, and it has the property that the elements are, it's under multiplication as you can see, and the elements are being looked at mod 5. So for instance, 3 times 4, I mean normally that's equal to 12, right? But when you look at it mod 5, well, that just gives you when you divide 12 by 5, you get a remainder of 2. So that means that 12 is really 2 in this group, right? And that's how we multiply everything else. Maybe another idea, 3 times 3 would be 9. What's 9 mod 5? 3 times 3 would be 9. Well, what's 9 mod 5? Okay, just wrote it weirdly, but 9 mod 5 will really be equal to 4 in this case, right? So that's what it means to multiply in this group, right? So now let's do some let's pursue some ideas here. So I'm going to introduce a bit of different notation. You may not have seen it before. So when I say, let's say 1G, think of it as 1 times G. That means that I get the group G and I multiply everything by 1. So in this case, that will give me 1 times 1, which just turns out to be 1. 1 times 2, which just turns out to be 2. 1 times 3, which just turns out to be 3. 1 times 4, which just turns out to be 4. Right? So, well, maybe let's try something. Let's actually create a table. So we're going to say this is 1, this is 2, this is 3, and that is 4. So 1G gives me 1 times 1. Actually, I want to write it down really correctly. So, okay, let's be more precise. Let's write this as, we have a table 1, 2, 3, 4. And we're going to start with 1G. 1G, we said 1 times 1 is just 1. 1 times 2 is just 2. This is 1G. Okay, a little error there. Let's erase this part. So we want this to be 1G. And we're saying that's 1 times 1, 2 times 2, 1 times 3, and now here we have 1 times 4. Right. So, and then we have 2G. What's 2G going to be? Well, 2 times 1 is just 2. 2 times 2 is 4. Mod 5 is just still 4. 2 times 3 is 6. What's 6 mod 5? Well, that's just 1. 2 times 4 is 8. So let me maybe put an equal here. Equals to this entire collection. What's 2 times 4? Well, that's just 8. What's 8 mod 5? That's just 3. Right? So the good thing about this group is that it's small. What's 3G going to be? It's going to be 3 times 1, which is just 3 mod 5. 3 times 2 is just 6, mod 5, that's 1. 3 times 3 is 9, mod 5, that's 4. 3 times 4 is 12, mod 5, that's 2. Alright? Again, we're working at things mod 5. And then the last element of the group is just 4G. Well, what's 4G going to be? Well, it's going to be 4 times 1, which is just 4. 4 times 2, which is just mod 5, that's 3. 4 times 3 is 12. What's 12 mod 5? Well, 12 mod 5 is 2. 4 times 4 is 16. Mod 5, that just gives us 1. Now notice something here. Well, 1G is just, well, it gives us the group. Remember, the group consists of the elements 1, 2, 3, 4. Right? Those were the elements of the group. Right here. 1, 1, 2, 1, 2, 3, 4. Those were the elements of the group. So over here we have we kind of notice something strange. When you look at 1G, we actually have the set, we get the exact set back. 1, 2, 3, 4. We have the group back. If we look at 2G, we get 2, 4, 1, 3. It's still the set 1, 2, 3, 4, but the only difference is that now the order has been switched. That is, technically, the way mathematicians call it is that 2G is a permutation of the set G. That is, it's the same set written in a different way, just the elements with the order switched. 3G is a permutation of G again, because you just have 3, 1, 4, 2. These are still the elements of G written in a different order. 4G is still the entire group G written in a different order. So what we notice here is that if you get any X element of our group G, then XG is a permutation of that group, a permutation, otherwise known as just reordering, right? So let's write it like this: permutation of the group. Why not? Right? That's a permutation of the group. So in particular, that's really interesting, because it means that we can associate the element 1 with 1, 2, 3, 4. We can associate the element 2 with 2, 4, 1, 3. That is, instead of think of 1 because in the group, right, in the group Z mod 5Z star, 1 is just the number 1, 2 is just the number 2, 3 is just the number 3, and 4 is just the number 4. However, we can also view it we can view 1, instead of viewing it as a number, we can view it as this permutation, this reordering, this reordering here, 1, 2, 3, 4 of the group G. 2 can then be associated with this reordering of which is 2, 4, 1, 3. 3, the number 3 could be thought of as not as a number, but rather as this permutation, this reordering of the group G. And 4 can be thought of as the reordering of the group G as 4, 3, 2, 1. So that means that when we write G equals to 1, 2, 3, 4, right here, when we look at the group G equals to 1, 2, 3, 4, this 1 could be thought of as standing for some permutation. 2 is standing for a permutation of the group G. 3 is standing for a permutation of the group, and 4 is standing for a permutation of the group. Right? So a natural thing to think about is, well, is this what happens when we multiply? Okay, fine, we can view each element as a permutation, but what happens if we multiply? For example, normally we saw before that 2 times 3 is just equal to 6, but mod 5, that's 1. What if we viewed 2 times 2 and 3 as permutation? So the permutation 2 times the permutation 3. Would that also give me the permutation 1? What would that mean exactly? Well, that would mean that is, for instance, what does it mean for two permutations to be equal? If A is a permutation, let's use other names. If sigma is a permutation and omega is a permutation, when we say that sigma equals omega, what we're saying is that, because a permutation is really just a function, we're saying that sigma of x, that is, if we plug in x into the function, should give us omega of x. If two functions or two permutations are equal, it means that when you put in an input, they give you the exact same output. Both of them, the same inputs give you the same outputs, right? The image, the domain, all of them are the same. So now what we want to think about is the permutation 2 times the permutation 3, does that really give you 1? The way to check that is to pick individual elements from the group. So remember, our group G has the elements 1, 2, 3, 4. That's our group. Now, all we need to check is, for instance, is 2, here we're looking at composition. Is the permutation 3 composed of the permutation 2? If you get this permutation here, and then you plug in, let's say, the number 2. What does that give you? What does this mean, first of all? It's just composition of functions. Like, for example, if I told you what's f of g of x, you tell me first apply g, then apply f. Another way of writing it is like this: f of g of x. That's another way to write the same thing. It just means apply g to x, and then whatever answer you get, apply f to it. That's the same here. So what's 2, the permutation 2 composed with 3, what does it do to the number 2? Well, in this case, it's going to take the number 2. Okay, so first, what this means is that we are looking at 2 composed with 3, and then we plug in the number 2. Right? Just like this, f of g of x. This is 2 of 3 of the number 2. Well, what's 3 of 2? Well, that's just what does the permutation 3 do to the number 2. So we just need to check on our table here. Well, 3, okay, so 3 takes in the number 1 and gives us 3. 3 takes in the number 2 and gives us 1. 3 takes in the number 3 and gives us 4. So what does 3 do to the number 2? It gives us the number 1 back. So that means that the permutation 3 of 2 just gives us 1. So then this becomes 2 times the permutation 2 just applied to 1. What's the permutation 2 applied to 1? That means what does the permutation 2 do to the number 1? From the table we see that 2 gets the number 1 and gives us 2 back. So in a sense you say it fixes 2. So that just gives us 2. Now what we're trying to check is that is the permutation 2 composed with 3 the same as the permutation 1? So let's see if 1, let's say, applied to 2, the permutation 1 applied to 2, let's see if that gives us 2. Well, obviously it does, right? Because as you saw from the table, 1 fixes 1. That 1 gives you 1 back. 1 when applied to 2 gives you 2. The permutation 1 when applied to 3 gives you 3. The permutation 1 when applied to 4 gives you 4. So what we're really saying here is that 1 applied to 2 is really going to just give us 2. So then the statement, if you view 2 and 3 as permutations, 2 times 3 as a permutation, we're saying that the permutation 2 of 3 applied to 2 is just going to give us 1 applied to 2. So 2 is sent to the same thing by this permutation and by this permutation 1. And if you actually do the calculation, you'll find that 2 does the permutation 2 of 3 for every element of the group. That is, if you apply, instead of 2, if you apply 2 of 3 to 1, if you apply 2 of 3 to 2, if you apply 2 of 3 to 3, if you apply 2 of 3 to 4, the answers will always be the same as when you apply 1 of 1, I mean this permutation 1 to 1, this permutation 1 to 2, this permutation 1 to 3, the same permutation 1 to 4. So what that begins to tell you, I recommend that you check, so at least you get used to doing these calculations. But what that ends up telling us is that 2 times 3, if you view 2 and 3 as permutations, this composition of functions is really the same as just 1. And it turns out this is true for all of these permutations. Right? So for instance, actually we don't know yet, right? So we're in doubt, right? So for example, if I just gave you 3 times 4, you tell me, if we look at 3 and 4 as numbers, well, that gives us 12. But mod 5, that's just 2. So 3 times 4 equals to 2 in this group. What if I viewed them as permutations? That is, I view 4 as this permutation, right? Maybe just 4 is this permutation, this reorganizing of things. It sends 1 to 4, 2 to 3, 3 to 2, 4 to 1. And what if I viewed 3 as this permutation here? It sends 1 to 3, 2 to 1, 3 to 4, and 4 to 2. Well, then in that situation, 3 times 4, the question we want to ask is, does that give us the permutation 2? And it turns out that it does. And the way to check it is the way we check that the permutation 2 composed with 3 gives us 1, the permutation 1. It's just checking element by element. What does 3 composed with 4 do to 1? And what does 2 composed with 1 do to 1? If, what does 2 do to 1? If both of them give you the same answer for every group element, then it means that this permutation, this composition of permutations equals to this composition of permutations. So really, okay, so like, okay, Christian, so this is curious. Why is this interesting stuff? Well, in this particular group, it means that we can view the group G as just 1, 2, 3, 4, or we can view the group G as permutations of the same set, permutations of the group, right? And then you're asking again, why is this so exciting? One of the reasons this is exciting is because permutations, remember, permutations remind us of the symmetric group, right? So permutations remind us of the symmetric group. Remind us of the symmetric group. There you go. So what permutations remind us of. So really, if each of these things, if 1 is a permutation, 2 is a permutation, 3 is a permutation, 4 is a permutation, and 1 we can think of as the identity permutation, because remember, 1 does nothing, right? 1 keeps 1 as 1, keeps 2 as 2, keeps 3 as 3, keeps 4 as 4. So really, we have permutations. So look at what we have here. We have a bunch of permutations, okay? We have an identity element, which is also permutation. And when you multiply one permutation with another permutation, you get another permutation within the same set of permutations. And you have inverses in this set of permutations. That's something you can check. Well, what you're saying is that, well, that's just the symmetric group S4, isn't it? S4, remember, is the symmetric group on 4 elements. All the possible permutations of 4 elements. So what we're really saying here is that, what kind of we're hinting at, we haven't proved anything yet. What we're hinting at here is that G is really the same as S4. Right? Usually for the symbol for same is this, kind of isomorphic. That means that although we might have written it differently, G is really the same as S4, right? And so a natural question to now ask is, well, is it really true that, so the conjecture here is, what guess can we make from this information? This was true for our special group here of just 1, 2, 3, 4. But the question can be asked generally. If G is a finite group, all right, let's start with that. If we have G is a finite group, is it true that G is, that if we pick elements, wait, I mean, you notice that if we get any group G and we pick some element x of G and we look at xg, well, first of all, is it true that xg is always a permutation of the group G? That would be the first question. Another question would be asking ourselves is, well, does it mean then that every group can be viewed as, is it true, like if I have a group containing the elements G1, G2, all the way up to Gn, is it really true that I can view these elements of the group as instead being permutations of this same group? Is each element a permutation of the group? Right. That's another, we haven't proved that yet. That's another question. And in particular, if we're going to be even more specific, are we saying that G, any finite group G, is isomorphic, right, is the same as the subgroup, the symmetric group applied to the number of elements in this group, right? Or maybe I'm going to write as just the symmetric group on the group. That is it the same as the symmetric group on this group? So another way of saying that is every group, is every finite group isomorphic to a subgroup H of the symmetric group Sn, whatever Sn stands for, right? Sn is just a symmetric group. And that's what Cayley's theorem tackles. And that's what so Cayley's theorem says, yes, this is true. but we need to investigate it for ourselves, and that's what the next video will be about, is answering this question of Cayley's theorem. Is it really true that any group G, any finite group, is always isomorphic to a subset of the symmetric group? So if you're interested in knowing this, then if you're interested in exploring this question, the next video is going to be exploring that. Otherwise, thanks a lot for listening.